Welcome to the course Structure Analysis. Myself Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So, today we are at the 8th lecture of Structural Analysis. So, last lecture we had discussed about the slope deflection concept. We derived the equation for slope deflection method. So, in today's lecture, by using the slope deflection method, how to solve the numerical problem, that's what today we are going to see. Okay, so this lecture is about analysis of beams using the slope deflection method, part 1. So, that one represents we are going to have the additional lectures which is 2 and 3 for discussing the numerical problems. So, at the end of this lecture, the student can able to apply the slope deflection concept for any continuous beams, and also they can able to calculate the support moments for the continuous beams. So, quickly take the example problem and then we calculate the final end moments. So, I am going to take a continuous beam which is going to have the 2 spans with the intermediate support. Let us give some name for this: support A, support B, support C. Span AB is having the eccentric point load. The intensity of the load is 50 kilonewton and it is located 2 meters from the left support, and this distance is 3 meters, and span BC is subjected to UDL throughout the span, and then intensity of this load is 24 kilonewton per meter, and span AB is 5 meters long and span BC also 5 meters long. So, I can say this beam is very simple to solve. So, one might ask, sir, it is a continuous beam and 2 spans are there. First span eccentric load is there, second span UDL is there. How this problem is very simple? The reason is, you see the support A and support C both are, the support A and support C both are fixed support. Why it is easy then? In the fixed support, slope is 0. So, very easily in the slope deflection equation, wherever the theta A coming, I am going to put 0. Wherever theta C is coming, I am going to put 0. That is why I told this problem is very, very simple. Okay, we will go step by step to solve this problem. Okay, step 1, I am going to calculate the fixed end moments. I am going to calculate fixed end moments, shortly FEM. Here FEM is a fixed end moments, it is not a finite element methods. Okay. So, I am going to take a part by part beam. Let us consider the span AB alone and consider both the supports are fixed. Okay. So, this is going to have the moment like this. Let us write, this is MFAB and this is MFBA. So, this is A and this is B. So, MFAB and MFBA. And what is the loading here? The loading here is 50 kilonewton and this is 2 meters and this is 3 meters, overall span is 5 meters. Okay. So, this and all is a simple formulas we are going to substitute. So, its moment direction is anti-clockwise, I need to consider minus sign, and the formula is WA B square by L square. So, simply substitute it here. The W value is 50 here, A is nothing but this one and B is nothing but the second span. Okay. So, A is 2 and then B is 3 meters, B square divided by L is 5. So, 5 square. What I am getting here is minus 36 kilonewton meter. In similar way, I am going to apply the formula for the MFBA. The formula is WAB. So, here the square term will come for A and L square. Both the formulas are not same, it is a different one. Here you can see B is having the square, and here you can see the term A is having the square value. So let's substitute 50 multiplied by the A value 2 square and then 3 divided by 5 square. So I'll be getting the value of 24 kilonewton meter. In similar way, I am going to take the another span now. Let's take the span BC also here, and we are going to consider that span is fixed support. So this is B and then C having the moment in this direction. I am going to calculate first MF BA, and then here I am going to calculate MF CB. Sorry, this is not MF BA. So this is MF BC, MF BC and then MF CB, B to C and C to B. So BC, what is the loading condition? UDL throughout the span, and then the intensity of the load is 24 kilonewton per meter, and the span is 5 meters. The span is 5 meters. Let's write the equation. So this is minus WL square by 12. Here we are going to have, because the clockwise direction is positive, WL square by 12. Let's substitute the value. The intensity of the UDL is 24 and then span is 5 divided by 12. Similarly, here also plus 24 multiplied by L square is 5 square divided by 12. So what is the value I am getting here is 50 minus 50 kilonewton meter, and here plus 50 kilonewton meter. So in the summary, we are calculated all the fixed end moments here. Let's write all the fixed end moments here. MFAB equal to minus of 36 kilonewton meter, and then MFBA equal to 24 kilonewton meter, and then MFCB is equal to minus 50 kilonewton meter, and then MFCB equal to plus 50 kilonewton meter. So now we are calculated all the fixed end moments. Then what is the next step? In the next step, we are going to apply the slope deflection equation. So let's write MAB equal to, I am writing the equation for the first span. So MFAB plus 2 times of EI by L into 2 times of theta A plus theta B minus 3 del by L. Okay. So you know the problem is like this. We have a fixed support A and fixed support at C, intermediate span is B. So in A and C, the slope is 0. So slope at A is 0, thus directly I can put this value is 0, and in this problem the support settlement is not given, so therefore the 3 del by L also is 0, and then I am going to substitute the value of MFAB is nothing but minus 36 kilonewton. So minus 36 kilonewton plus whatever the things are there here, we have a 2 EI by L is 5 meters here. Okay, so 5 meters multiplied by, we only have the theta B. Okay, let's simplify further this equation. MAB equal to minus of 36 plus 0.4 times of EI into theta B. Let's consider this equation is a first equation. So quickly I am going to take the calculate for the MBA. So MBA is equal to MFBA. I am just writing the slope deflection equation plus 2 EI by L into 2 theta b plus theta a minus 3 del by L. No support settlement, so this term is 0, slope at A is 0. So, we will be having MFBA value is plus 24 kilonewton plus 2 times of EI by span is 5 meters. So, we will be having here 2 times of theta B. So, by simplifying this equation, I will be getting 24 plus 0.8 times of EI into theta B. Okay, so this is MBA. Let's say this is the second equation and we already have the first equation. So, two equations, this is the second equation. Let's solve for the BC. So, I am going to take now MBC. MBC is equal to the fixed end moment MFBC plus 2EI by L, okay, into 2 times of theta B plus theta C minus 3 del by L. So, C is a fixed support, so this term will become 0, there is no support settlement, this term will become 0. So, MFBC is minus of 50 kilonewton plus 2 times of EI by L is 5 meters, we having here 2 times of theta B. If you further simplify this equation, minus of 50 plus 0.8 times of EI into theta B. So, this is the equation 3. So, we have one more equation to solve, that is MCB. So, this is the value of MBC. So, let us solve for that also. MCB is equal to MFCB plus 2 times of EI by L into 2 times of theta C plus theta B minus of 3 del by L, okay. So, no support settlement 0 and support C is a fixed support, so theta C is 0. Let us substitute the remaining values. MCB is a fixed end moment is plus 50 kilonewton plus 2 times of EI by L is 5 meters and then we are having theta B here. Further simplifying this, I am going to have the MCB is equal to 50 plus 0.4 times of EI into theta B. So, this is the fourth equation. So, totally we have 4 equations, but we never found the value of the final moment so far. For that, we need to apply the equilibrium equations. Applying the equilibrium equations. Now, what is the equilibrium equations? For example, in our case, the beam is like this and we have an intermediate support A, B, C. The equilibrium equation is this one. So, MBA and then MBC, the summation of MBA and MBC is equal to 0 for equilibrium condition. So, the equilibrium equation is MBA plus MBC equal to 0. For example, the MBA in a anti-clockwise direction, if it is a minus 40, then MBC is a plus 40, so it will become 0. Okay. So, this is for example, it is not a real value. So, this boundary, this equilibrium condition I am going to apply to get the final moments. So, write down the equation once again, MBA plus MBC equal to 0. So, let us apply the boundary, this equilibrium condition, then we will see what we are going to get it. So, already we have equations 1 to 4. So, I am going to have the substitute the equation MBA here, which is 24 plus 0.8 times of EI into theta B and then MBC value is minus 50 plus 0.8 times of EI into theta B. So, we will be having adding this minus 50 and minus 24, I will be getting minus 26, and adding 0.8 plus 0.8 will become 1.6 EI of theta B. So, theta B is equal to 26 divided by 1.6 times of EI. So, in more simpler manner, theta B is equal to 16.25 divided by EI. So, we got the theta B value. So, here after getting the final moment is very simple, because our equation 1 to 4 is comprises of theta B. We are going to substitute this theta B to the first equation, second equation, up to 4 equation will be getting all the moments. Let us see that quickly. So, first I am going to substituting theta B in the equation 1. So, we know the equation 1. Equation 1 is, I am just writing the equation 1, MAB is equal to minus of 36 plus 0.4 times of EI into theta B. So, MAB is equal to minus of 36 plus 0.4 times of EI into theta B already we know, which is 16.25 divided by EI. You can see here we already calculated theta B is 16.25 EI. We just substituted here. So, here EI will be get cancelled. So, we will be having MAB is equal to minus of 29.5 kilonewton meter. So, in the similar way, I am going to substitute theta B in the second equation now, in the equation 2. So, just write the equation 2, which is MBA. So, MBA equal to 24 plus 0.8 times of EI into theta B is our second equation. Let us substitute MBA equal to 24 plus 0.8 times of EI into theta B is 16.25 divided by EI. So, EI will be get cancelled. So, we will be having MBA equal to 37 kilonewton meter. So, we have 2 more equations to substitute this theta B. Let us quickly substitute. So, I am going to take now the third equation. So, substitute theta B in the equation 3. So, what is the equation 3? Equation 3 is MBC equal to minus 50 plus 0.8 times of EI into theta B. So, MBC equal to minus 50 plus 0.8 times of EI into theta B is 16.25 by EI. So, EI will be get cancelled. We will be having MBC is equal to minus of 37 kilonewton meter. Similarly, I am going to substitute theta B in the equation 4. So, equation 4 is MCB equal to 50 plus 0.4 times of EI into theta B. So, MCB is equal to 50 plus 0.4 times of EI into theta B is 16.25 by EI. EI will be get cancelled. So, MCB is equal to 56.5 kilonewton meter. So, we got all the values. Let us write all the values here. MAB is equal to minus 29.5 kilonewton meter MBA equal to 37 kilonewton meter, MBC is equal to minus 37 kilonewton meter, and MCB is equal to 56.5 kilonewton meter. So, we applied the slope deflection method and then we calculated all the final end moments of the continuous beam, which is statically indeterminate. We applied the boundary condition that also satisfied here. You can able to see MBA, the summation of MBA and MCA is MBA and MBC is 0. So, MBA plus MBC equal to 0, we can able to see here, minus 37 plus 37. Okay. So, this is the end of the 8th lecture. So, we learned how to calculate the final end moments. In the next lecture, we are going to see another example problem, and also we are going to see how to draw the shear force and bending moment diagram for this example problem. So, thanks for watching this lecture. Thank you.